Hi all, welcome to the next session. So in this session we'll be dealing with image compression. How we'll do the image compression using singular value decomposition. So first we'll see just the algorithm of how to do the image compression. And suppose you are given with the matrix A, and let A represents a matrix A will be representing a particular image, and what we do is we'll compute A transpose A and we'll find the corresponding eigenvalues and eigenvectors, and we can also get the singular values. And after the singular values we'll just arrange them in the descending order. Okay, and we'll form the matrix sigma. Until here they are the same procedure, similar to the way we found the singular value decomposition. And now we do is we'll compute the right singular values v right singular vectors v from eigenvectors of A transpose A. We'll just see how we do that. We'll just calculate ui's, which is equal to 1 by sigma I a v I, and then we'll just write A is equal to u sigma v transpose. We know the singular value decomposition process. And to do the compression, what we do is suppose the rank of A is equal to R, and choose k less than R and keep only the first k singular values. Okay, if we need to do the rank 1 compression, what we do is we'll just find A1. And what is A1? A1 is sigma 1 u1 v1 transpose. Okay, and if we need to get rank 2 compression, what we do is A2 is equal to sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose. Okay, that's a formula to get the rank k compression. So let's do. I hope the procedures are clear, since this up to step 6, in fact up to step 7 we have the same procedure similar to finding the singular value decomposition. So let's see one problem. Here in this question, an image is represented by the following 3 by 3 matrix of pixel intensities. You are given with A, and if suppose you are given a picture, will just frame the pixel intensities as a matrix, and the matrix is given here, and you are asked using only the largest singular value construct a rank 1 approximation A1 of the matrix A. Okay, so you are asked to find rank 1 approximation. So what you will do is first we'll just, you are given with A, and what is A transpose? A transpose is equal to, just write the first row as the first column, then the second row as the second column, then the third row as the third column. And see, you can see A and A transpose both are same. A is equal to A transpose. So A transpose into A is in fact equal to A square. And on doing this, you have a particular matrix here. Okay. And using this matrix, we need to get the eigenvalues. So yeah, finding the eigenvalues A transpose A minus lambda I, will just find the matrix and take its determinant to be equal to 0. And now by equating this, you can just try take the determinant of this particular matrix and see, equate it to 0 and see that this values of lambdas are 49, 1 and 1. Okay, you will be getting a cubic equation, and on solving that we can get your eigenvalues to be 49, 1 and 1. And now what you do, is we'll find the corresponding singular values. So sigma I is equal to root of lambda I, and you have sigma 1 is equal to root of 49, which is 7, sigma 2 is 1, and sigma 3 is also 1. So we have this matrix, sigma is equal to, first entry will be 7, second entry is 1 and 1. Your A was 3 by 3, so your sigma is also 3 by 3, and you have your sigma. Now what we do is we'll just find the corresponding eigenvector. When lambda is equal to 49, A transpose A minus 49 I into V is equal to 0. So what is the matrix A transpose A minus 49 I? It's given by this particular matrix. And on choosing V to be xyz, you can see you will have an equation like this. Okay. And you need to solve this to get the values of xyz, and this concept was already discussed in finding the eigenvector. I will just, you can take 16 common from first equation, so that will be minus 2x plus y plus z is equal to 0. Similarly, just do for the second equation, so that would be x minus 2y plus z is equal to 0. And what you can do is you just multiply by 2 on both sides, so you will be having what you will have 2, this will be 2, this will be 4 and this will be 2, and you can just add both the equation. So that would be 0x, and on adding this minus 3y plus 3 z is equal to 0. So from here you have y is equal to z, is it? If y is equal to z, what happens? You just substitute in this equation. Let me call it as 2. On substituting y is equal to z in 2, you will have minus 2x plus 2y is equal to 0. So you will have x is equal to y. So on comparing all this, you will have x equal to y equal to z. Okay. So just for your vector v is both in fact equal to x, y, z. So that will be equal to 1, 1, 1. So that is your eigenvector, and your eigenvector should always be normalized. So what to do? If you are having your v is equal to 1, 1, 1, to normalize it, divide it by square root of 1 square plus 1 square plus 1 square, which is equal to 3. So I'll just divide it by root 3 and get this one. Okay, so you have your eigenvector, and now what we do is you will find ui. Okay, ui, since we need rank 1 compression, you need to get what is u1 and v1. Okay, so to get u1, you need to find what is a v1. So get just multiply them and get your a v1 will be 1 by root 3, 7, 7, 7. Okay, and what you need to do, you will just have to divide it with sigma 1, which is 7. So that will be basically here it's 7. Since it's division, just take the 7 to inside, so that will be 1, 1, 1. Inside it will become 1, 1, 1. So the your u1 will be equal to 1 by root 3 into, so you have your a with you, your a is there, just a minute, yeah, you are having a with you, your u1 with you, your v1 with you. So you know how to calculate, sorry, you know how to calculate your a1, right? A1 was given by sigma 1 u1 v1. So let us see what is your a1. A1 is equal to sigma 1 u1 v1 transpose, and just substitute. Your sigma 1 is 7, your u1 is this one, and v1 transpose, just do this. Okay, and on multiplying this 1 by root 3 into 1 by root 3 will be 1 by 3, and it will be 7 by 3 on the outside, and on the inside it will be 1, 1, 1. Okay, taking 7 by 3 is approximately 2.333. So you can just take it to inside and have. So this is your rank 1 matrix. Okay, your a1 was given by sigma 1 u1 v1 transpose, just substitute and multiply to get your a1. This is your rank 1 approximation. Okay, so now let's see one more problem. Here we are asked to find, consider the grayscale image represented by 3 by 3 matrix. Your a is equal to 2, 0, 1, 0, 1, 0, 1, 0, 2, and form a rank 2 approximation a2 using the two largest singular values. That is your question. So what you can do is, first you will compute A transpose A, and by computing A transpose A, you have this matrix, and you will just calculate the eigenvalues corresponding singular values, and then you will find the eigenvector v1 and v2, then correspondingly u1 and u2, then just do sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose. For that you have A transpose A, then you just calculate the determinant and find the eigenvalues. Just do the determinant and equate it to equal to 0. So you have lambda equal to 1, lambda equal to 1, and lambda equal to 9 are the eigenvalues. You can see as shown in the steps how to get them. Okay, then after factorizing, you have lambda 1 is equal to 9, and lambda 2 is equal to 1, and lambda 3 is equal to 1. So the first two largest eigenvalues are 9 and 1. So using that, you can find the singular values. Sigma 1 is equal to root of 9, which is 3. Sigma 2 is equal to root of 1, and sigma 3 is also equal to root of 1. And now we'll find the eigenvector v1. So to get v1, we have A transpose A minus 9i is given by this particular matrix, and this matrix into xyz equal to 0. What gives you, first equation will be minus 4x plus 0 into y plus 4z is equal to 0. So from here you have x is equal to z, and from the second equation you have y is equal to 0. Okay, so your y is always 0 and z and x are equal. So just give 1 to the x value, so that will be 1, 0, 1. So you can just normalize it by dividing by the norm, which is root 2. So your v1 will be 1 by root 2, 1, 0, 1. Okay, this will be your eigenvector. I'm just rushing through because these concepts are already discussed in the area of eigenvalue and eigenvector. So you have your v1 and now we need v2 also, because we are asked to find rank 2 compression. So what we do is we'll just find we have the second eigenvalue and we find A transpose A minus I, and we have this matrix and we do x y z, and here you have 4x plus 4z is equal to 0, so here comes x is equal to minus z. Okay, so and also in the from the second equation you have nothing, and third equation also remains the same, so which means y and x are free. So you'll choose your y to be 0 and your x to be 1 and negative 1. Okay, 1, then if x is 1, your z will be negative of that, so you have this negative 1, and by dividing by the norm you just normalize second vector and you have v2. Okay, now what you do, you find corresponding u1. U1 is a v1 by sigma 1, and you can just try that is 1 by 3, and just do a v1. Okay, a into v1, just do it. I think we have done it before, so just paste it here, a v1 divided by sigma 1, and similarly do a v2 by sigma 2. Okay, and after doing that what we have is, okay, we have E2 is equal to sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose, and first we'll find sigma 1 U1 V1 transpose, then you have this particular matrix, then you have sigma 2 U2 V2 transpose, and you have this particular matrix. Okay, just do the matrix multiplication and you have this, and for E2 you just add them. Okay, and you have your A2, the rank, the second rank, rank 2 compression matrix is given by 2001 000 102. This is your rank 2 compression. Okay, now we will just see a question from noise filtering. So suppose a noisy signal or image is represented by A is equal to the matrix 2 1 0 1 2 0 0 0 0. You will have to use SVD to remove noise by keeping only the largest singular value. So what we do is, we'll follow the same procedure. First we'll compute the value of E transpose A, and A transpose A is given by the matrix. You can just multiply to get 5 4 0 4 5 0 and 0 0 0. This will be our A transpose A, and you'll be finding the eigenvalues of A transpose A. And to get that, we'll do determinant of A transpose A minus lambda I is equal to 0. We'll form the equation. So by forming the matrix A transpose A minus lambda I, you will be getting this matrix, and by finding the determinant of this matrix you have lambda is equal to, by solving this quadratic equation you will be having lambda is equal to, okay, you will have to note that your equation when forming the determinant will be lambda into 5 minus lambda the whole square minus 16 is equal to 0. Okay, so from here you will be having one eigenvalue lambda is equal to 0, and to get the next eigenvalue, oh, you can just simplify this quadratic equation to get this one, and just find the eigenvalues as lambda is equal to 9 1 and then 0. Okay, you have lambda here, you should note that. Okay, and now we have the eigenvalues. We will find the corresponding singular values, and the singular values are given by the root of the eigenvalues. Root of 9 is equal to 3, and the second singular value is root of 1, and third singular value is root of sigma 3, which is equal to 0. And now we will find the corresponding eigenvectors. For that we have the eigenvalue is 9, and corresponding singular sorry, eigenvector is given by A transpose A minus 9 I into V is equal to 0. So by forming A transpose A minus 9 I, you have this particular matrix, and then that particular matrix into x y z. What will be that? This into x y z will give you, this into x y z will give you other eigenvector v1 is equal to 1 by root 2 1 1 0. Okay, so you can just verify that the eigenvector corresponding to the eigenvalue lambda is equal to 9 is given by v1, which is equal to 1 by root 2 1 1 0. And now since you have the eigenvector, you can just find the vectors uy by given by the equation avi by sigma I, since we need the rank 1 approximation using the largest singular value. Okay, we were asked to approximate using the largest singular value, that is we need rank 1 approximation. So you can just find a1, the approximation is given by sigma 1 u1 v1 transpose. So you just need u1, so for that you can do a v1 by sigma 1, and on doing that you have your a here, your 1 divided by sigma 1, which is 3, and also you have your v1, and on multiplying you have your u1 is equal to 1 by root 2 110. And now to get the a filtered, that is your rank 1 approximation matrix, which is a1, it is equal to a1 is equal to a filtered matrix is given by sigma 1 u1 v1 transpose. So that is your 3 u1 v1 transpose, and it's given by your u1 was equal to u1 and v1 is equal to 1 by root 2 110. Okay, therefore by multiplication you will get the 3 by 3 matrix, which is your filtered matrix. Okay, so that's it about the session. So hope you got how to do the rank 1 and rank 2 approximation, where either if it is in the case of noise filtering or in the case of image compression, we follow the same procedure. Okay, we'll just find if we need the rank 1 approximation, we'll just choose the largest eigenvalue and the corresponding eigenvector and the corresponding u1, and then do the sigma 1 u1 v1 transpose. If we need the rank 2 approximation, we do sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose. Okay, that's the procedure we follow for the approximation, and that's it. We will conclude the session now. Thank you.